In this video, we're going to talk about and discuss quadratic functions. All right. Before we get to that, let's actually do the definition of a quadratic function. All right. Quadratic functions are functions of the form f of x equals ax squared plus bx plus c. All right. And so in our last video, we talked about solving quadratic equations. And remember, quadratic equations are equations in the form ax squared plus bx plus c equals 0. Notice that there is a number on the other side, and I can write all of my variable parts and my constant terms on the other side. The difference in this case is now we have a functional value. This is when we think input, output. Remember, a function is a relation where each input value corresponds to or gets assigned to one and only one output value. And that means that instead of having a number on the other side, of course, when you think input, output, you will, there's actually another variable here because that's going to be changing depending on what x equals as well. All right. And so remember, we always said that y was the same thing as f of x once we know that something is a function. And so this is the difference between the equations and the function. The function is the input-output relationship, whereas an equation is something that we're going to solve for. Now, of course, the thing that can get a little confusing is that we can change or turn equations into, functions into equations. But that's what we're dealing with now. This is the initial setup. So we won't always be solving for a variable. This function is just representing a relationship between the input and the output. Some examples of functions are an example like this. F of x equals 2x squared plus 5x minus 9. Notice that your input value is x. Whatever is output is your output value. That's going to be your y value. And remember, when we're using function notation, you don't necessarily have to use f of x, right? We can do something like h of t, which we're going to see very often in this in some of the application problems. In this example, we have h of t equals negative 16t squared plus 64t plus 96. In this example, t is our input variable here. And our output for y is called h of t. And we're going to see an example where we're using that notation there instead of f of x. But now that we know what a quadratic function is, I want you to be able to evaluate a quadratic function. It's the same thing as evaluating a quadratic expression or a polynomial. But let's look at this example here. It says for f of x equals x squared plus 12x minus 52, find f of negative 5. Notice here that this negative 5 is in the space of my f of x when I'm defining this function here. And so if I want to find f of negative 5 and simplify that, I've got to put negative 5 in for x everywhere I see an x, which is here, and simplify. And that'll give me my answer. So let's do that. F of negative 5 equals a negative 5 squared. Notice that I put the negative 5 in parentheses, the negative as well, because if I don't, I'm going to get an incorrect answer. I'm squaring the negative and the 5. That'd be plus 12 times negative 5 minus 52. Of course, I can simplify. That's going to be a 25 minus 60 minus 52. And 25 minus 60 minus 52 is negative 87. So f of negative 5 equals negative 87. Let's look at this next example. It says, let f of x equals x squared plus 11x minus 26. Find all values x for which f of x equals 0. Now, we got to think here what we're doing in this problem. Of course, they've defined what our function is algebraically in x squared plus 11x minus 26. That's what our function f of x equals. In this case, this is a little different. Notice here that they're not giving us the x coordinate. They're actually giving us the output. They're saying that find the x values for which f of x equals 0. I want to know which input values cause our function to have an output of 0, right? Well, the output, f of x, is here. So I'm going to replace f of x with 0, and then I get an equation, kind of like we had in the last section, where we have x squared plus 11x minus 26 equals 0, and we can solve for x there, all right? And so we're going to do that. I'm going to have 0. I'm going to replace f of x with 0, and that's going to equal x squared plus 11x minus 26. Of course, if you wanted to write your equal 0 on this side over here, that's perfectly fine. But you're going to solve it the same way, right? There's no GCF. There's a 1 in front of the x squared. So I'm going to go ahead and do my double set of parentheses, put my x in my first spots here. All right, and I want to find two numbers that multiply to give me this negative 26 here, but add up to 11. Those two numbers will be positive 13 and negative 2. All right, and so those are two factors or two things that multiply. They have a product of 0. If I want to solve for x, I can set them both equal to 0, right? So that's going to be x plus 13 equals 0. And my other solution is going to come from x minus 2 equals 0. All right, I can subtract 13 from both sides here. I'm going to get x equals negative 13. And I can add 2 to both sides to this equation here. And I'm going to get x equals 2. So these are the x values, negative 13 and 2, for which f of x equals 0. That means if I plug these x values in, my y coordinate should be 0. All right? That's the purpose of doing this type of example here. Let's look at another example. It says, let f of x equals x squared minus 7x minus 20. Find all values x for which f of x equals 58. This one is very similar to the last example, except this time we want f of x to equal 58, right? Remember, when we give you f of x, we're giving you a y value, right? Your functional value, and you're finding your x value. And so here, I'm going to have 58 equals x squared minus 7x minus 20. All right, now this one's a little different because we don't have a 0 on that other side. But if I want a 0, all I have to do is subtract 58 from both sides. By subtracting 58, I get 0 equals x squared minus 7x minus 78. And now I want to factor so that I can create my two linear equations and solve. No GCF, 1 in front of the x squared. All I need to do is find two numbers that multiply to give me negative 78, but add up to a negative 7. Those two numbers will be negative 13 and a positive 6. Okay? And so if I want to solve for x, I set each of these factors equal to 0, right? That's our 0 factor property. And I solve for x. Add 13 to both sides here. I'm going to get x equals 13. And subtract 6 from both sides here. And I'm going to get x equals negative 6. So my two values of x that cause my function to have an output of 58 would be 13 and negative 6. All right, and so I want you to be able to do all three of those types of examples that we just did, because when we get to some application problems, those are going to be the highlights of what we're going to be doing in order to solve some of those application problems. One of the main application problems that we're going to discuss in this section involves what we call projectile motion. And I'm going to talk about projectile motion in just a little bit, but I want to talk about the graph of a quadratic equation so that we can kind of know what the graph looks like. We know what the graph of a linear equation looks like. It's a line, but we want to be able to know what the graph of quadratic equations looks like. And so I'm going to use this quadratic function here, f of x equals negative x squared plus 5. Again, remember, anytime I have f of x, we can write it as y. All right. One of the best ways to graph something when you don't know, you have no idea what the graph looks like, is to graph by plotting points, right? That's when we get us a table, create a table, an XY chart. You have y equals negative x squared plus 5 so that we can come up with ordered pairs. And when I really don't know, I'm going to use about 5 ordered pairs. And what I'm going to do, I'm going to plug those x values into this function here, all right, or into this equation here, and it's going to tell me what the y value I get, all right? For instance, if I plug in negative 2 for x, notice that that's a negative. That's going to be a negative 2 squared plus 5. Negative 2 squared is 4, but I got this negative on the outside here, right? So that's going to be a negative 4 plus 5. And negative 4 plus 5 equals 1. So I get the ordered pair with the x-coordinate negative 2, positive 1. All right, I can do this for each of the others. All right, that's going to be a negative 1 plus 5, which equals 4. Negative 0 squared plus 5 equals 0 plus 5, which equals 5. Negative 1 squared plus 5, right? Negative 1 plus 5, which equals 4. And I'm going to plug in 2 for x, which we get 1. And so I have all of my ordered pairs, and now I'm going to graph them on this xy plane here. Negative 2, 1 from my origin, I go to the left 2 and up 1, and I'll have this point here. The point negative 1, 4 goes from the origin, go left 1 and up 4, and I have this point here. 0, 5 from my origin, I just go up 5. The point 1, 4 to the right 1 and up 4 from my origin. And then the point 2, 1, right 2, up 1. And I have this point here. All right. And so what this graph is going to look like is a curve like this. And it is curvy. I don't want that to be pointy. But it looks like an upside down U. All right. Now, every single quadratic equation is not going to look exactly like this one. This one right here is upside down, because there's a negative in front of this x squared. If there was not a negative in front of that x squared, then it would be right side up. It'll look something, go along that path right there. The reason why I did this specific example is because the projectile motion applications that we're going to involve in this section, or solve in this section, involve graphs that looks like this. All right. Let's talk about projectile motion. All right. Projectile motion problems, they deal with the height of a free-falling object after it has been thrown or dropped with an initial speed. All right. And so if you think about just, let's say you're standing on the ground right here and you throw a ball or a rock. All right. That's what I mean by a projectile. An object that can't stay in the air by itself, meaning the only force that's acting on it is the acceleration due to gravity, right? If you throw that rock in the air, it is going to go up to a certain height, and then it's going to turn around and go back down, all right? And if you notice, this type of shape here is very similar to the graph of this function that I've graphed up here. All right, the upside down parabola. And so that's what we're going to be talking about in this section. Now, since it has this shape here, that means we can model it using a quadratic function. Now, what I'm going to do is I'm going to draw an XY plane, for instance, right? My XY plane, I'm going to have something that looks like this. So the x-axis, and I'm going to have a y-axis. When I deal with these projectile motion problems, instead of having my x-axis and calling it x, I'm going to have a t-axis, and the t is going to stand for time. All right, and it's always going to be in seconds for what we're going to do in our course. All right, so how many seconds? Instead of my y-axis being y, I'm going to call it an h-axis, and that stands for height. And our height is always going to be in feet. So as you can see, this model here kind of tells me the height of the object that I'm throwing in the air at a certain time in seconds. For instance, if I notate this axis, and I'm going to count by fives here. I could use the graph of this function here, or this quadratic equation here, in order for me to determine the height after a certain time period. For instance, after, let's say, 2 seconds, right? If I go to 2 seconds on my x-axis and find a point on my graph, it looks to be somewhere around here. I know the height of my graph by finding the y-coordinate to this point right here. So let's say that that's about 17 feet. So after 2 seconds, right? 2 seconds is exactly right here on my x-axis. If I go to the point on the actual curve at 2 seconds, it has a y value of about 17. So I can say that after 2 seconds, that rock that I threw in the air should be 17 feet above the ground. All right. I can find the maximum height. All right. The maximum height seems to be located here. It seems to be 24 feet, approximately 24, 25 feet. And it occurs, or it happens, at about 3.6 seconds. All right. So that's how we can use this graph to gather information about this quadratic function and how it models the actual projectile motion. Now, what we're going to do is we're not going to really be using the graph. The graph is very helpful because it is visual. What we're going to be doing is, now that we know what the graph looks like, we're going to be using algebra to help us figure out how to solve these projectile motion problems. Let's look at an example of that. In this example, it says a football is kicked up with an initial velocity of 64 feet per second. The football's height above the ground in feet after t seconds is given by the function h of t equals negative 16t squared plus 64t. All right, so instead of giving you a graph, I'm giving you the actual equation that models the graph, right? But what we do know is that since this equation does model the graph, or the situation that's going on, it's going to be a picture that looks something like this. This is going to be my time in seconds as my x-axis, and my y-axis is my height axis, right? In part A, it says, how high above the ground will the ball be after 1 second? All right. So what we want to try to find is the height. All right. Remember, your height is your y coordinate, right? And your y is always your output, right? So we want to find the output, or the y coordinate, when the input is t equals 1, right? It tells me 1 second. So all I'm doing is finding the y when x is 1. All right, if you want to think in x or y. So we're finding h of 1. All right, so all I have to do is plug 1 into this function wherever I see a t, kind of like our x coordinates, and it's going to spit out my y coordinate, which is our height. All right, so that's our h of t. Right, and so I'm going to do that. I'm going to have a negative 16 times 1 squared plus 64 times 1. Negative 16 times 1 is negative 16. And 64 times 1 is 64. And so if I add negative 16 and 64, I'm going to get 48. Okay? Notice this is a height. It represents my output, which is a height. And my height is always in feet. So my units would be 48 feet. Let's go to part B. It says, how long will it take for the ball to land on the ground? This was a little bit more complicated and a little harder to think about. So I'm going to go back to this diagram over here, right? Initially, my ball is starting on the ground. It's going to go up for a certain period of time. Then it's going to go all the way back down. And it's going to hit the ground right here, right? So basically what we're trying to find out is what's the t-coordinate or the x-coordinate of this point, all right? How long or how many seconds does it take for this ball to get to this point right here? Well, if you think about it in terms of your axes here, okay, I'm going to draw this axis. Sorry about that. Notice that these y values represents your height, all right? And every point that's on this x-axis, or I should say my t-axis here, has the exact same y-coordinate, right? I don't know the x-coordinate. I'm just going to call it t. But at this point right here, I do know the y-coordinate, right? So from the origin, all I do is go to the right a certain number of units, but I don't go up or down, right? Whenever we don't go up or down, we know we have a y-coordinate of 0. All right. And so in this example, when I want to figure out when something lands on the ground, all I need to figure out is when the height equals 0. All right. So another way of asking this is to say find t. So we're going to find t when the height, which is given by h of t, equals 0. All right? And so let's do that. Now all we're going to do is go up here, replace h of t with 0, and then solve for t. I get 0 equals negative 16t squared plus 64t, and all I have to do is solve for t. All right? Remember, we're still talking about quadratic equations here. Remember, to solve this, we have to factor. In order for us to factor, the first step is to think about the GCF, right? So a lot of the other examples, we didn't have a GCF, but in this example, we actually do. Our greatest common factor would be a 16t, but since that 16 is, that negative is in front of the 16 as our leading coefficient, I'm going to factor out a negative 16t. All right, when I factor that out, remember, we put in parentheses what we get when we divide our original polynomial by negative 16t, the GCF, and that'll be a t minus 4. Now, if you look, I'm actually done factoring, right? Because I can't do anything else with this t minus 4. So I have two things that multiply together to give me 0. I'm going to set them both equal to 0 and solve for t. I get negative 16t equals 0 or t minus 4 equals 0. These are giving me my two solutions. I'm going to divide both sides by negative 16. When I divide both sides by negative 16 here, I get t equals 0. And I'm going to add 4 to both sides here. And when I do that, I'm going to get t equals 4. All right, now notice here that I have two solutions. I have t equals 0 and t equals 4. Only one of them is going to be my solution. And I want to go back up here to the diagram so that we can think about it. In this diagram, I've drawn my quadratic function like this, right? T equals 0 is right here. So t equals 0 is right here, and t equals 4 would be right here. The reason why I got t equals 0 is because that's where my ball or my rock was initially kicked from. It goes in the air, stays up in the air for 4 seconds. So my solution, that is the actual solution to this problem, is 4 seconds. We don't want to say 0 seconds because 0 seconds is our initial time. All right. And that concludes our video on quadratic functions.